Okay, I want you to picture a black hole. Seriously, close your eyes if you can. What do you see?
I think I know where you're going with this.
If you're like most people, or, if you've seen the movie Interstellar, you're probably seeing this perfect black sphere. And around it, this glowing flat disk of light.
Like a vinyl record made of fire.
Exactly. A vinyl record made of fire.
Yeah.
It's the iconic image.
It is. It's on T-shirts. It's in all the textbooks.
Okay.
And for a long, long time, that was the standard model in astrophysics, the thin disk.
Right. But I've been digging into this new review paper we're covering today. It's The Influence of Low Beta Plasma by Aslan Shah, just out in 2025. And if I'm reading Shah right, that whole vinyl record picture, it's not that it's wrong exactly, but it's missing the main character of the story.
It's missing the director. The classic models, they sort of gave us the set design, but they didn't really explain the plot. Shah's paper is basically saying, stop obsessing over the gas.
And start looking at the magnetic field.
Exactly.
Which, I have to be honest, feels a little counterintuitive. We're talking about black holes, the ultimate gravitational monsters.
Right.
Infinite density, points of no return. You'd think gravity is the only force that matters down there.
Yeah.
So why are we suddenly talking about magnetism?
And that is the paradox, gravity. It sets the stage. It pulls everything in, yes. But gravity is surprisingly simple. It just pulls.
Right.
The force that actually creates the friction, the light, the incredible heat, and those huge jets we see shooting across galaxies, that's magnetism. And specifically, we're diving into this really extreme environment called the low beta regime.
Low beta?
Yeah.
It sounds like a software update that's still got some bugs.
Far from it. In plasma physics, it's the state where magnetic fields, they stop being polite passengers and they start driving the bus.
Okay, so that's our mission for this deep dive. We're going to tear apart this Aslan Shah paper and figure out what happens when magnetic fields take over a black hole. But first things first, let's set the scene. The paper focuses on a Schwarzschild black hole.
We're keeping the math clean to start. A Schwarzschild black hole is the simplest kind you can imagine. It's a perfect sphere, it's static, and really importantly, it doesn't spin.
Which is pretty rare in the real universe, I'm guessing, but it's a good baseline so the math doesn't get totally out of control.
Exactly. It gives us a perfect laboratory. You've got the event horizon, the point of no return, and a little bit further out, you have the ISO.
The ISCO.
The innermost stable circular orbit. You should think of it as the edge of a waterfall. Outside the ISCO, you can orbit in a nice circle forever. But once you cross that line,
the current's too strong.
Gravity becomes too steep. There are no stable orbits. You just plunge.
You're in free fall.
Correct. So that's the gravity part. That's the bowl. But Shah's review is all about what fills that bowl, and specifically this one variable called plasma beta, the Greek letter beta. And this is probably the single most important concept for you to get today. If you understand beta, you understand the whole machine.
Okay, so break it down for us. What is beta actually measuring?
It's basically a tug of war. On one side, you have gas pressure. That's the thermal energy of all the hot plasma trying to expand. On the other side, you have magnetic pressure, the force from the magnetic fields.
So beta is just the ratio.
It's simply gas pressure divided by magnetic pressure.
Okay, simple enough. Gas over magnetism.
So let's imagine a high beta situation. Let's say beta is 100. That means the gas pressure is 100 times stronger than the magnetic pressure.
So in that case, the gas is clearly the boss. The magnetic field is just, being dragged along.
It's like leaves in the wind. The magnetic field lines are weak, floppy, they get twisted and pushed around wherever the gas wants to go. And this is actually the classic model.
The Shakura-Sunyaev disk from the 70s.
That's the one. It just assumed the magnetic fields were, negligible.
But the whole point of this paper is that as you get close to a black hole, that assumption is just wrong.
Totally wrong. It gives you a nice, clean picture, but it doesn't match what we see. As you get closer to the horizon, and especially in that atmosphere above the disk, the magnetic fields get amplified. We enter the low beta regime. Beta drops below 1.
Way below 1.
Down to 0.1 or even 0.01.
So the whole ratio flips. Now the magnetic pressure is 10 or 100 times stronger than the gas.
And the physics changes completely. The magnetic field lines aren't leaves anymore. They become stiff. Think of them like steel cables or high-tension wires.
So instead of the gas pushing the field
pushes the gas.
That is a huge shift in the power dynamic. And the paper goes right into how this changes the actual shape of the accretion disk. Which brings us back to that vinyl record image.
Which we now have to throw out.
Right, because gravity wants to flatten it. I mean, that's why Saturn's rings are so thin, right? spinning things flatten into a disk.
Gravity's pulling everything toward that central plane, yes. In a high-beta, gas-dominated world, the gas pressure just isn't strong enough to fight that vertical pull.
So gravity wins. It squashes the disk into a thin sheet.
Geometrically thin, like a CD. But in our low-beta world,
You've got this other force pushing back.
you have this intense magnetic pressure pushing back. Magnetic fields hate being compressed. So as gravity tries to crush the disk flat, the magnetic pressure pushes up. It provides vertical support.
So the disk inflates.
It puffs up. The paper describes the inner part of the disk transitioning from a thin sheet to a geometrically thick torus.
A torus. So we're talking about a donut.
A glowing, super hot, magnetized donut. The paper mentions the height to radius ratio can jump up to 0.5. That means the disk is literally half as tall as it is wide.
That's not a record anymore. That's a truck tire made of plasma.
A very, very hot truck tire. And the internal structure changes too. In a thin disk, you have a really sharp density gradient, super dense in the middle, then almost nothing. But inside this magnetic donut, the density profile flattens out. It becomes this chaotic, churning, more uniform soup.
Which is fascinating because it completely changes what you'd see if you could get close. It's not a thin line, it's a glowing wall. But I want to shift to the engine part of this. Because a puffed-up disk is cool, but the real mystery isn't that black holes have disks. It's that they actually eat.
Ah, yes. The accretion problem.
Yeah. I mean, we just assume stuff falls into black holes, but physically, that's actually really hard to do, isn't it?
It's incredibly difficult. It all comes down to angular momentum. Imagine you're an astronaut orbiting the Earth. You're moving sideways at, 17,000 miles an hour?
Right.
Gravity is pulling you down, but that sideways speed keeps you missing the Earth. You stay in orbit.
To fall down, I have to slow down. I have to hit the brakes.
You have to lose that angular momentum. An astronaut fires a retro rocket, but a cloud of gas doesn't have rockets. So for 50 years, the big question was, how does the gas lose its momentum? What's the friction?
And just normal friction like gas molecules rubbing together, that's not enough.
Not even close. Space is basically a vacuum. The gas is way too thin. If you relied on normal viscosity, it would take longer than the age of the universe for a black hole to eat a single meal.
So we need a better brake. And I'm guessing, based on where this is going, the brake is the magnetic field.
It's the MRI, the magnetorotational instability. This is the mechanism that Shaw's paper points to as the absolute driver of accretion.
The MRI sounds medical.
Oh, yeah.
So explain it to us. How does a magnetic field act like a brake?
Okay, so picture two blobs of gas in the disk. One is a little closer to the black hole and one is a little farther out. Now, because of orbital mechanics' Kepler's laws, the inner blob is moving faster than the outer blob.
The inside track is faster.
Got it. Now, imagine there's a magnetic field line connecting them. In a plasma, these field lines act like physical tethers. They're like a spring or a rubber band stretching between these two blobs.
So the fast inner blob is physically connected to the slow outer blob.
Exactly. So the fast inner blob tries to race ahead, but that magnetic spring stretches. It pulls forward on the slow outer blob, speeding it up.
And if you speed something up in orbit, it moves outward.
It moves outward. The outer blob gets flung further away. But, and here's the key, the spring also pulls back on the fast inner blob. It acts as a drag. It slows it down.
And if you slow down in orbit,
You fall, you lose your angular momentum and spiral inward, and this magnetic tethering is happening everywhere in the disk, all at once. It creates this massive churning turbulence that's constantly shipping momentum outward and allowing matter to cascade inward.
that is such a cool mental image. So it's not really friction. It's more like magnetic tension. The paper talks about Maxwell stresses versus Reynolds stresses. Is this what that means?
Precisely. Reynolds stress is just, normal fluid turbulence like water churning in a river. But Maxwell stress is this magnetic tension we just described, the tension of those rubber bands. And Shaw's review makes it clear that in the low beta regime, the Maxwell stresses they completely dominate. The magnetic springs are doing all the heavy lifting.
And that's really important for efficiency. The paper mentioned something called RIAFs.
Radiatively inefficient accretion flows.
Yeah, it's a mouthful.
What does that mean, radiatively inefficient?
It just means the gas is so thin and so hot that it can't cool down by glowing. It can't radiate its heat away effectively. In the old gas-only models, if you couldn't radiate, the accretion would just stall, the gas would get hot and just sit there.
But because we have the MRI and these powerful magnetic fields,
The accretion just keeps on going. The magnetic fields force the matter into the black hole, even if it can't cool down.
Okay.
It lets the black hole feed in the dark, so to speak.
Well, in the dark is a relative term, because while the disk itself might be bad at glowing in, say, visible light, the paper says these things are pumping out something else entirely, hard X-rays.
Ah, yes. The mystery of the corona. This was one of the coolest parts of the paper for me. We think of a corona, we think of the sun, that wispy halo you see in an eclipse. I didn't realize black holes had them.
They do, and they are way more violent. The paper explains that this low-beta disk is basically a factory for building coronas.
Okay, so how does that work? What's the process?
It all comes back to those magnetic springs. Remember we said the MRI creates all this chaotic turbulence?
Right.
Well, just imagine those magnetic field lines getting twisted and braided and tangled up by all that churning.
Like headphones in a pocket.
But much, much worse. Eventually, the tension becomes too much. The magnetic field lines snap and then realign themselves into a lower energy state. It's a process called magnetic reconnection.
It sounds kind of gentle reconnecting.
It is the opposite of gentle. It is an explosion. When those lines snap, they release a huge amount of stored magnetic energy instantly. It acts like a little particle accelerator, and it heats the local plasma to billions of degrees.
Billions. With a B.
We are talking 10 to the 9, 10 to the 10 Kelvin. This creates a cloud of super hot relativistic electrons that sort of boils up above and below the main disk.
And that is the black hole corona.
That's the corona.
And that's what's making the X-rays.
Indirectly, yeah, through a process called comptonization.
Walk us through it.
So you have the main disk, the donut, which is warm. It's emitting these soft, lower energy photons. Some of those photons drift up into the super hot corona.
Okay, so a soft photon walks into a bar full of relativistic electrons.
And it gets punched hard. The electrons are moving near the speed of light. When they collide with that photon, they transfer a massive amount of energy to it. It gets a kick.
And it goes from a low-energy soft photon to a high-energy hard X-ray.
Exactly. So when our telescopes see this powerful hard X-ray spectrum coming from a black hole, they are actually seeing the signature of that magnetic violence.
It all connects. Without the low beta fields, no reconnection. No reconnection, no hot corona, no hard X-rays. The model just fits the data. But the paper doesn't stop there. It takes this whole idea of strong magnetic fields and asks, okay, what if we turn the dial all the way up to 11? What happens if the field gets too strong?
We enter the realm of the MAD.
The magnetically arrested disk.
It's a great acronym, but what does it actually look like?
Okay, imagine pouring water down a bathtub drain. That's normal accretion. Now, imagine you stick a high-pressure fire hose directly into the drain, blasting water upward.
The water can't get down, it backs up, it chokes the drain.
That is an MAD. The magnetic field lines get dragged inward with the gas, but they pile up near the event horizon. They get compressed and compressed until their outward magnetic pressure is strong enough to fight the inward pull of gravity.
Wait a second, gravity is supposed to be infinite at the horizon. How can a magnetic field stop that?
Well, it doesn't stop gravity, but it stops the flow. It creates a magnetic barrier. The black hole effectively chokes on the magnetic field.
That sounds unstable. Extremely. The whole system becomes this violent, sputtering engine. The gas can't flow in smoothly anymore. Instead, it has to punch through this magnetic wall in what the paper calls interchange instabilities.
Like bubbles bursting through the surface of water.
That's a great analogy. Heavy blobs of gas crash through the magnetic wall and fall in, while big bundles of magnetic flux burst outward to escape. It's chaotic. But, and this is the huge payoff, this MAD state is the most powerful engine in the universe for one specific thing.
Jets.
Relativistic jets, those incredible beams of matter that shoot out of galaxies at 99% the speed of light.
We've all seen the pictures. They stretch for thousands of light years.
Yeah.
And the paper is saying you need this low beta MAD environment to launch them.
You need a launch pad. This is the Blanford-Payne mechanism.
How does that work?
So think of the magnetic field lines as stiff wires that are anchored in the spinning disk. As the disk spins, the wires spin with it. Now, if you put a bead on a spinning wire, what happens?
Centrifugal force flings it outward. It slides up the wire.
The gas particles are the beads. The magnetic field lines are the wires. But for this to work, the wires have to be stiff. If the magnetic field is weak, high beta, the gas just bends the wire. No jet. You need the incredible rigidity of the low beta field to act as a railgun that flings matter out into space.
So that famous picture of the M87 black hole, the orange donut, We know that thing has a massive jet. Are we looking at a low beta system there?
We were almost certain of it. In fact, the Event Horizon Telescope didn't just take a picture, they measured the polarization of the light.
Which tells you about the magnetic fields.
It tells you the direction the magnetic fields are pointing. And the data from M87 shows these beautiful, ordered, spiral magnetic fields right at the edge. It's a textbook confirmation of the MAD model.
We're literally taking pictures of the physics we're talking about right now. That's incredible.
It's a triumph of theory meeting observation. It really is.
I want to bring this all down to a slightly smaller scale before we finish. The paper also talks about X-ray binaries. These are the smaller star-sized black holes that are, eating a neighbor star.
Right, and these are really dynamic systems. They change their behavior over time.
Yeah, a paper calls them states or moods. They can be quiet, and then they can be really loud. How does this magnetic theory explain that?
It offers this beautiful, unified framework. Astronomers have basically observed two main states, the high-soft state and the low-hard state.
Okay, let's decode that. High-soft.
That happens when the accretion rate is really high. There's a flood of gas pouring in. Because there's so much gas, the gas pressure is high.
So high gas pressure means high beta.
Exactly, high beta. And remember what happens in high beta. The magnetic fields are weak, the disk is thin and flat, it glows with soft thermal heat, and crucially, there's no jet.
Because the magnetic wires are too floppy to launch anything.
Precisely. But then for whatever reason, the fuel supply drops, the gas pressure fades.
And the magnetic pressure takes over.
Yeah.
We switch to low beta.
We enter the low hard state, the inner disk puffs up into that hot torus, the corona forms, the hard X-rays turn on, and suddenly, bam, you get a powerful, steady jet.
So the transition from a quiet black hole to a jet-spewing black hole is really just a switch from gas control to magnetic control.
That is the elegant conclusion of Shaw's review. It all comes down to beta. That one little number can tell you the geometry of the disk, the kind of light it emits, and whether or not it has a jet.
It's just amazing that one ratio can dictate the behavior of the most powerful objects in the cosmos.
It really is. We've moved from a universe where we thought gas was king to realizing that, really, magnetism is the power behind the throne.
So to wrap this deep dive up, we started with the old view, the flat, gas-dominated vinyl record. And now, thanks to work like Shaw's, we see the reality. A low beta universe where magnetic fields puff the disk into a donut, drive the inflow of matter with magnetic tension, snap and reconnect to cook up a billion-degree corona, and act as the railgun for cosmic jets.
That is a perfect summary.
But I feel like there's one loose end here.
There is always a loose end in astrophysics.
The paper focuses on Schwarzschild black holes, the non-rotating ones. But we know real black holes spin. And when you add spin to physics, things usually get crazy.
They get exponentially more powerful. And this is the final thought I think we should leave everyone with.
Go on.
We talked about how strong these magnetic fields are around a still black hole. Strong enough to stop the gas from falling in. Now imagine you take those same stiff magnetic field lines, those steel cables, and you thread them through the event horizon of a black hole that's spinning at nearly the speed of light.
You're twisting the cables.
You're twisting space-time itself. The spinning black hole grabs those magnetic field lines and drags them around with it. This creates a dynamo effect called the Blandford-Znajek process.
And what does that do?
It extracts energy directly from the black hole's spin. It uses the magnetic field to literally break the black hole, converting its rotational energy into pure power.
So the jet isn't just powered by the gas falling in anymore.
No. It's powered by the spin of the monster itself. If the low beta fields we talked about today are powerful, the fields around a spinning Kerr black hole are. They're world eaters. They launch jets that can punch through entire galaxy clusters.
We've really just scratched the surface of the power of magnetism.
We have just opened the door.
A terrifying and awesome thought. The invisible hand of magnetism shaping the dark heart of the galaxy. Thanks for listening to this deep dive into the low beta universe.
My pleasure.
Keep looking up and stay curious. We'll see you in the next deep dive.